Okay, this video we're going to talk about approximation theory, in particular the orthogonality principle. And so let's go ahead and jump in. All right, so projection and inner product. This is just a review of chapter 2. How does the inner product represent a projection? So if you recall, this comes from, so this is basically the Cauchy-Schwarz inequality. So it's equality as long as we have this fudge factor, cosine of theta. And if we have a unit vector, so if the norm of y is equal to 1, then the projection of x onto y, this projection here of x, orthogonal projection onto y, is going to be the norm of x times the cosine of theta, because the norm of y is equal to 1. So in 2D, basically an inner product represents the length of the projection of x along the direction of a unit vector y. Now, in general, if y is not unit vector, or if x is not unit vector, then it's a projection, but it's a non-orthogonal projection of one vector onto another. It represents essentially how much of x, how correlated are x and y, how much of x is inside of y, how much does of x is represented by y. So these are meanings, I guess, of the inner product, but it all relates to this projection. And if one of the vectors, if the vector that we're projecting onto is unit length, then it's an orthogonal projection. Okay, so let's consider the following approximation problem. Suppose you have a Hilbert space S. So we've got this Hilbert space S, and we've got some x here. Now, suppose we've got a set of vectors, and we look at the span. So there's some set of vectors here, and this is going to be the span of P1 up to Pn. So we have some, again, a closed subspace inside of S. And each of these elements are inside of our elements of S. So now the question is, let's find an x naught, or an x hat, that is in the span of those vectors that minimizes this error. So this would be the error, would be the norm of x minus x hat. Can we find an x hat that minimizes that? And of course, the projection theorem says that, we need to find a particular, that the element here will be such that this vector is orthogonal to everything inside the span of x. Okay, so this is the approximation problem. All right, so x hat is going to be, since x hat is in the span, we say x hat is in the span of P1 to Pn. What does that mean? It means that it's a linear combination of those vectors. So that's exactly how we would write a linear combination of elements of of vectors P1 up to Pn. So this is implied by the x hat is in the span of P1 up to Pn. That's what we mean when we say that. Okay, now the projection theorem. So if we form this error, E is going to be x minus x hat, which is exactly x minus C1 P1 up to Cn Pn. Now this thing is going to be minimized if E is orthogonal to the span of all these vectors. Okay, so that's just the projection theorem. All right, so E is going to be orthogonal to the span of those vectors. What does it mean? It means that E is orthogonal to any vector inside of the span of any linear combination. And in fact, we can say that it has to for sure be orthogonal to each of these vectors. So certainly this we have this implication because P1 and Pn are in the span. We can actually go this direction because anything that's in the, if this is true, you know, if this statement is true, then when we say, you know, if we want to take the inner product with anything else in the span, you would have C1, P1, you know, plus up to Cn, Pn, and that's going to be equal to the inner product of, well, that'll be C1, inner product of E with P1, I guess C1 bar, plus all the way up to Cn bar E with Pn. And, you know, each of these guys are equal to 0. So that's equal to 0. So, in fact, if this is true, if it's orthogonal to each of the vectors P1 to Pn, then it's going to be orthogonal to anything in the span of P1 up to Pn. So this is an if and only if statement. Okay, so that is true. I guess we've already shown that it's true if, oh yeah, so now what we're going to do is say, okay, well, we're just going to plug in what the error is. The error is x minus P1 up to Pn, inner product with P1, and that's true all the way down, inner product to Pn. So maybe the dots should go like that. All right, so then, you know, we can pull out each of these vectors and write it as, you know, x inner product with P1. So we're going to have x inner product with P1, and then we'll have minus C1 with P1, all the way up to Cn, Pn, and then x with P1, x with Pn, and then C1, P1 with Pn, all the way up to Cn, Pn with Pn. Okay, now we're going to take these equations and write them in matrix form. So we're going to take, you know, these vectors, I guess, move them to the other side of the 0, so there's no minus signs, and then we'll switch the order. So these guys become a vector, x with P1 down to x with Pn, and this guy, you know, becomes, notice we have a P1 with P1 times, so the first row here is going to be C1, P1 with P1, all the way down to Cn, Pn with P1. And, you know, similarly, we can write this thing in terms of the row of that matrix. So if we define this matrix here, so this matrix R is going to be essentially the inner product or the cross inner products of all of these elements, P1 with P1, you know, on the diagonal we'll have P2 with P2 down to Pn with Pn, and then the first row will be inner product of all the vectors with P1 down to the nth row, all the vectors with Pn. And this matrix R is this is a very important matrix. Notice that this is going to be a matrix even if the vectors P1 to Pn are, say, functions or sequences. They don't have to necessarily be vectors in, say, complex, you know, n space. They can be functions, but we still get this matrix equation because the inner product makes all of this stuff finite. Okay, so we end up with this equation RC is equal to P, and this matrix R is called the Gramian of the set P1 to Pn. So this is a definition. You know, R is called the Gramian of the set. So we define it. Given a set P1 to Pn in vectors in this Hilbert space S, the Gramian, and this actually can just be a vector space. It doesn't have to be a Hilbert space. The Gramian of the set is defined in this way. And notice that because if we were to take the transpose and complex conjugate things, we would get RH is equal to R. Because, again, PI with PJ is going to be PJ with PI, as long as we complex conjugate. All right, so we have also the following theorem from Moon. The Gramian R is positive definite. Remember, a vector R is going to be positive definite, so R is positive definite if and only if x, h, r, x is positive for all x not equal to 0. So it's positive definite if and only if this set of vectors are linearly independent. So the vectors are linearly independent. R is positive definite. By the way, R positive definite also means that it's full rank. All the eigenvalues are positive. All of these things are equivalent. We'll show this later on, actually, when we talk about eigenvalues. So the Gramian R is positive definite if and only if the set of elements P1 up to Pn are linearly independent. And I guess we can prove that. So let Y be an S. So we want to show that YHRY is, in fact, strictly greater than 0 if P1 to Pn are linearly independent. So we can write out what this means. It means that this vector of Y complex conjugate up to Yn complex conjugate times the Gramian times Y1 up to Yn. That's just YHY. Now if we multiply, these two vectors together, we're going to get, we'll have Y1 with this vector down to Yn bar with that vector, and that's going to be this sum, Y1 up to Yn, and we're summing, of course, on this index. And then all the way over to the last element, again, we'll be summing on, this element, so there's where Pi is, and the Yi's come down, and then this is now an n dimensional row vector, and this is a column vector. So when we multiply, we're going to get now Y1 times this thing down to Yn times this guy. So we'll have the sum. So we're going to sum, I guess, on i's. These are still i's, and now when we multiply this vector out, we'll sum on j's. So we'll have all of the yj's, and now P1 up to Pn and Y1 up to Yn. There's the j. It'll be on the first element, and then I is still this second element. So we get something that looks like that. And this guy is, in fact, we could have written this out as, let me get rid of that comma. And, this is this vector yj up to pj with itself. This is j equals 1 to n, I equals 1 to n, and we could have easily, I and j are just dummy variables. So this is just going to be the norm of that vector squared. And of course the norm is always positive, so we've shown that in fact this is greater than or equal to 0. So R is always positive semi-definite. We haven't said anything about linearly independent. So now what we want to do is show that, so it's always positive semi-definite, and now we want to show that if each of these PI's are linearly independent, then this is not greater than or equal to 0, it's just greater than 0. All right, so, and again, it's an if and only if. So we have to show that if R is positive definite, then the vectors are linearly independent. And if the vectors are linearly independent down here, that R is positive definite. Okay, so suppose that R is positive definite, then when we write it like this, we have to have greater than 0, not greater than or equal to 0. So since the norm is 0, if and only if the thing inside of it is 0, we have to, since the norm is strictly greater than 0, this vector here has to be non-zero. And it's non-zero for, for every, this would be R in CN, and that means that these vectors are linearly independent. Remember, what does it mean for a set of vectors to be linearly independent? It means that the linear combination of those vectors, the only way it's 0 is if each of the coefficients here are 0. So since this thing is non-zero, for every non-zero element of y, these vectors have to be linearly, these vectors are linearly oh, I'm sorry, these vectors are linearly, this should be independent. Yeah, in other words, the only way for this thing to be 0 is if every element here is 0. And since it's non-zero for non-zero y's, they have to be linearly independent. Yeah, this is a typo. All right, conversely, suppose that they're linearly independent, but R is only positive semi-definite. So R positive semi-definite implies that there exists some y, so that when you do the norm here, this thing is equal to 0. And it's equal to 0 for a non-zero y, which means this vector has to be equal to 0 for non-zero. You know, this is for non-zero yi's, for some non-zero yi's, which means that it's in fact linearly dependent, which is a contradiction. So we had this assumption that these things were linearly independent, but R is only positive semi-definite, and this contradicts that fact. So in fact, R has to be, it can't be positive semi-definite, which implies that R is positive definite. Okay, so that all brings us to the orthogonality theorem. And the orthogonality theorem is essentially a restatement of the projection theorem, but using all of these this nice notation that we've just built up. All right, so suppose that P1 to Pn are vectors in our Hilbert space S. And let X be some element of S. So again, here's our picture. This is S, and we have, you know, inside here the span of P1 up to Pn, and X is out here. And what we want to do is we want to find, you know, we want to find our element here, X hat, that minimizes the difference, E equals X minus X hat. So we're solving an optimization problem. So let X be in S, let E be defined as, you know, the error vector between X hat and X. So in other words, E is equal to X minus X hat. Then E is minimized when it is orthogonal to each of the data vectors. So in fact, you know, it has to be orthogonal to each of these P1 to Pn. Or equivalently, we can write it in terms of this RC equal to P. In other words, the error is minimized. So when C, these coefficients here, satisfy this Gramian equation. And the proof is just using the projection theorem. Now we could have gotten to the same answer using calculus without using the projection theorem. And let me just walk you through how you would do that, because it's interesting in and of itself. So this is essentially a alternate proof, I guess. You know, really this is an alternate proof of the orthogonality theorem. Okay, so again, we let X be, or the error be X minus a linear combination of all of our data vectors. And we want to find all of these coefficients, C, that minimize the error. So it's the same problem. We have S, we have, this is our span of P1 up to Pn, and we have an X. We want to find, you know, X hat in here that minimizes the error. All right, So the first thing to note is that minimizing e squared is equivalent to minimizing e. It doesn't matter if you have a squared, term, because the element that will minimize e squared is the same element that minimizes the norm of e. All right, so now let's look at what is the norm squared of e. So we plug in what e, it's the inner product of e with itself. This is the inner product of e with itself, and we plug in what e is here, and then we multiply everything out. Inner product of x with itself gives us norm of x squared, and then we've got the inner product of x with these guys, and we'll have to pull those out to get, we'll have to pull the coefficients out to get complex conjugate. And then we have CP with these guys, and so it's 2 times the real part. So this notation is the real part of CI, the sum of CI complex conjugate with the inner product of x with PI's. And then we've got this term with that, and so we'll have the sum of CJ's and CI bars and PI PJ's. So if we write all this in terms of matrix notation, we can write this guy as CH times RC, and we can write this guy as, notice that this is our vector P, and so this is going to be CH times P, so we have 2 times the real part of CH times P. So the norm of E squared is the norm of that guy. And now what we want to do is we want to minimize this. We want to find C that minimizes this guy. So calculus says, to minimize E squared equal to that guy, we just differentiate this expression here with respect to C and set it equal to 0. And it'll be a local minimum if the second derivative of this guy is positive semi-definite. So that's what calculus tells us. So the question is, how do we take derivatives with respect to a vector? Okay, so I could go through this, but it's in Moon Appendix, and maybe I could answer questions tomorrow. We could derive this expression if we wanted to. But Moon has these 2 expressions. When you take so if you have the real part of CH times P, and you take the partial with respect to C complex conjugate, you're going to get 1/2 P. And you have to take it with respect to complex conjugate, or you get a complex value here. Okay, and then if we take the partial of CHRC with respect to C complex conjugate, we're going to get RC. Okay, so we take the partial then of this guy, and notice, the real part here gives us 1/2 times P, so we'll have a 2 here, so we'll have a minus P, and then the partial of this guy with respect to C complex conjugate is just going to be RC, and there's no C in there, so when we take the partial with respect to C complex conjugate, it's going to be equal to 0. So we'll get our minus 2P and then 2RC equal to 0, and when we solve, we put this guy on the other side, divide by 2, and we get R times C is equal to P. And if you take the second partial now, so we'll take the partial of this guy with respect to C complex conjugate, and what do we get? We get, this vector 2R. And this guy, we already know that R is positive semi-definite. And in fact, if all of the basis vectors are linearly independent, then this is strictly positive. So calculus tells us that the solution of this matrix equation, RC equals P, minimizes the norm of E. That's the exact same equation we got using the projection theorem. So we've shown essentially a proof of the orthogonality theorem using 2 different approaches. All right, so I want to do some examples, and do some examples. Let's see, I think most of these are matrix examples. we'll do a polynomial approximation here soon. Okay, so I want to do an example. Matrix representation. All right, so suppose that each of these elements, so in other words, let pi be an element. I guess these could be complex n space, not necessarily real. Yeah, everything here holds for complex space, so we can go ahead and do that. So if we go ahead and stack these vectors, suppose these are all, they're column vectors, dimension n. We can stack all of those, into a matrix. So P1 is the first column, P2 is the second column, Pn is the last column. And then, our coefficients, we write that as a column vector again. So x hat, now we can write x hat as Cj, Pj, and that is, in fact, we can write it as a matrix A times our coefficient vector C. So the error now is going to be x minus AC. All right, so the orthogonality theorem says that this error, that C is minimized when this error is orthogonal to all of the column vectors. So we can project that E onto each of these column vectors, and it has to be equal to 0. Okay, so that's the inner product of E with P1 down to the inner product equals 0, E with Pn equal to 0. So we can write it in this way, and the inner product now in Cn is going to be, the inner product of A with B is going to be BHA. So this inner product is equal to 0 is just P1H times x minus AC equal to 0 all the way down to Pn. All right, now if you notice that that AH, so since A is equal to P1 up to Pn, when we take the transpose and complex conjugate it, then we're going to have P1H as the first row of AH down to PNH. So now the column vectors form the rows. Notice this is going to be 1 by n, and this guy is all n by 1. So now we're going to stack all. This is like a row vector. We're going to just stack all these together, and we can write these vectors, or this set of equations, as AH times x minus AC equal to 0. And then if we multiply this out, we have AHX here, and we move it to the other side. And then AH times AC gives us AHAC, like that. And this is for matrix, if we have vectors, if our column vectors are basically our data vectors are just column vectors, then the Gramian R is equal to AH times A. And then this vector P on the other side is just AH times X. Okay, so we can now this equation we can invert as long as R is positive definite. And so if P1 to Pn are linearly independent, then R is greater than 0. It's positive definite, which means it's going to be invertible. And so we can just invert this equation over here, and our coefficients are going to be AHA inverse times AHX. And since we have back here, way back here, we have that x hat is equal to A times C. We can now plug in what C is. So x hat is going to be, it's A, and then this is C. And we get that x hat is AHA inverse times AH. And this is the best approximation of x inside of the span of P1 to Pn. Now, it's a fact that this matrix here, this guy, AH inverse times AH, is an orthogonal projection. It's a projection matrix. You know, you can do PA squared is going to be AHA inverse AH times AHA inverse AH. So notice here's an AHA times AH inverse. So that's identity. So we'll have AHA inverse, and that's all identity AH, and that's just PA. So this is in fact a projection matrix. That's a typo. All right, and this thing is called a pseudo-inverse, by the way. We'll talk later on about pseudo-inverses. Actually, yeah. All right, so we'll talk about these later on. In fact, this is the pseudo-inverse. All right, so that's what the orthogonality theorem gives us for matrices, and that's really the one of the most important cases. We also have a lot of these cases where we're trying to approximate things with functions, and so let's look at polynomial approximation. So suppose that you're given a real function f. Okay, so you have some function and you want to approximate it by an mth order polynomial on this interval 0 to 1. All right, so you take your basis vectors. You know, these are going to be your P1, P2 up to Pm. Actually, I guess this would be P0, P1 up to Pm. This would be Tm. And then you're going to let f hat be a linear combination. So this would be t raised to the m. All right, so if we define, remember we saw that inner product on functions can be defined as the integral of f of t times g of t. So let that be the inner product. Then the projection theorem, or the orthogonality theorem, says that, I guess this would really be the orthogonality theorem. Theorem implies that the best approximation is when the error, so we form, the error is equal to f minus f hat, when the error is orthogonal to all of the basis vectors, down to Tm, like that. So, yep, I've got typos everywhere. I'll fix these later. And that's m. So now we can rearrange this expression in terms of the, a Gramian expression. Again, this gives us a matrix, to find the coefficients. There's only a finite number of coefficients. And so to find the coefficients, it turns out to be just a linear algebra problem. So the Gramian is still an m by m vector, and these inner products are developed, are found by taking the integral of functions, but we end up with a matrix equation, and then we have polynomials, a finite dimensional vector, and then again, we take our original function that we're approximating and project that onto each of these basis vectors, and we get RC is equal to P, and then we can find we can, as long as the original basis vectors are linearly independent, we invert R and find the coefficients, and that will give us this approximation, the best approximation in this set. All right, another example, linear regression. Suppose you have a whole bunch of data points and you're trying to fit a line to these data points. So here's all your data points. This is some x1, x2, or I'm sorry, x1, y1. This maybe is x2, y2. Okay, so you have a bunch of data points, and you want to fit a line. So the line is going to be, y is equal to ax plus b. So the question is, how do you find a and b that minimizes the squared error? So if this is x and this is y, then you would be taking you'd take all of these little errors. This would be, that would be E1, E2, because the error is the difference in the y component. E2, that would be, E3, and we want to minimize, you're minimizing the sum of these squared errors over all of your data points. I equals 1 to n. Okay, how do we solve this problem? All right, so for each data point, we have an error. yi minus a xi minus b, and yeah, that's for every data point. And now the error, so if we let y be the basically a column vector of all of our y's, and then we let e be this column vector with all of your errors, and then you let c be the two things we're trying to find, a and b, and a is always multiplied by your x's, and b is always multiplied by 1. So this A matrix is going to be all of your x's and all of your 1's. We can write this equation then as e, and then this gives us y, and then these two guys give us AC, minus AC. So E is going to be equal to y minus AC. Now we have to project error onto the data vectors, which are in this case are going to be the columns of A. So again, this is just turns out to be a matrix equation, right? It's a matrix equation. So we're going to get when we project, in other words, we're going to take E with, if we called this guy A1 and this guy A2, E with A1 has to equal 0, and E with A2 has to equal 0. And this formula gives us, AH times E equal to 0, and E is going to be y minus AC. So we can rearrange that as AHAC equals AHY, and then we invert this matrix here. This is going to be our Gramian R. We invert the Gramian as long as, A1 and A2 are linearly independent. So as long as these vectors, all of the x's are not the same element, there's different x's, then they'll be linearly independent. And we invert and we get our coefficients. And then, and the coefficients, these are going to be, of course, A and B. So that gives us the least squares. Okay, so there is